Hey, calculus. All right, fundamental theorem of calculus. Maybe you recall the fundamental theorem of algebra. It said that if you have a polynomial p of x is equal to x to the fourth minus 3x squared plus 2x minus 1. And I said, how many solutions are there to that polynomial? There are 4. And it also learned that it can be factored. And we also learned that if there's a solution that is complex, say 2 minus 3i, then 2 plus 3i is also a solution. That was the fundamental theorem of algebra. Well, there's also a fundamental theorem of calculus, and the fundamental theorem of calculus really changed the world forever. And I'd like to give you a brief reasoning. This is not a proof, but it's really interesting. It has to do with this guy. F prime of x is equal to f of x plus h minus f of x all over h. And just to help you understand what that means, we used to say, if f of x is equal to x squared, we would, use that f of x plus h minus f of x all over h, and we would take the limit as h goes to 0 to find that derivative. And in this situation that you come out with, in this situation you come out with 2x, because you know what that derivative is. So let me just write it out. Suppose that the limit is h goes to 0 of x plus h quantity squared minus x squared over h. If I asked you to tell me what is f and what is f prime, you should be able to look at that and do that. So for example, you know that f is x squared, and you know the derivative is going to be 2x. Pretty straightforward, simple as can be. So we'll try another one. Suppose we have the limit as h goes to 0 of x plus h cubed minus x cubed over h. Well, as you look at that, if I ask you what is the function, you would say x cubed. If I ask you what is the derivative, you would say it would be 3x squared. So that's pretty good. Last one. Suppose I said the limit as h goes to 0 of e raised to the x plus h minus e to the x all over h. You would say the function is e to the x, and you know the derivative is e to the x as well. You don't even need to determine the limit, because you identify the function and you identify the derivative. So what I'm going to do here is I'm going to give us a reasoning behind why the fundamental theorem of calculus is what it is. And the fundamental theorem of calculus has to do with not derivatives, but integrals and area. And so I'm going to start here at this spot. We're going to call this A. Then we're going to go to that spot. We'll call that x. And we're going to go to that spot. And we're going to say that this distance here is h. So this would be x plus h. Okay? And we're going to write an expression for this. We're going to say that the area, we're going to call it area, from x to x plus h. So I'm referring to the area right here. That's going to be equal to the area of the entire thing, so from a to x plus h, minus the area from a to x. Okay? So if you want to find the area of the red, you take the whole green thing and you subtract off this black part, you would get the red. Okay? So that's what you would get. Well, what I would like to do is I'd like to approximate that area. Okay? I'd like to approximate it right now. And I'd like to use a rectangle. I'd like to approximate this area right here. We know that the width is h. And now we want to know the height. Okay? And I actually drew that rectangle backwards from what I wanted to. I'm going to draw a left side rectangle. Very good. So I know that the width is h. In order to determine the height, I plug in x and I get f of x. That's the height. So in other words, that area is approximately, so I'll write h times f of x is approximately a from a to x plus h minus a from a to x. What's interesting here is we divide by h, you get f of x is approximately a from a to x plus h minus a from a to x all over h. And if you draw h closer to x, so you make h closer to 0, it's going to become more accurate. So in fact, the limit as h goes to 0 of a from a to x plus h minus a from a to x all over h is in fact going to be f of x. This thing right here should look very familiar. It's identical to what we have up here. And you're going to have to stare at that for a while. You're going to have to stare at that for a while and convince yourself. But what it means is this. What does that say about f of x? Well, f of x is the derivative of the area. So this guy I've circled in green here, f of x, which is this thing right here, it turns out that that's the derivative of this thing I've circled in blue, the area function. And what that means in reverse is the area function is an anti-derivative of the function. This is going to make everything so cool. We'll get to fundamental theorem calculus part 1 in a second, but actually we're doing part 2 today. You might ask, what is an antiderivative? We've already talked about that. We'd say that, you know, if you have f of x equals x to the nth, then f prime of x is n times x to the n minus 1. But at the end of first semester, we said that big F, or the antiderivative, is going to be x to the n plus 1 over n plus 1. So that means if we want to find the area, we simply do an antiderivative instead of a derivative. Let's start by finding the antiderivatives. Here, the antiderivative, or big F of x, is going to be x to the 4th over 4. Done. Big F of x is going to be 5x to the 5th over 5, or x to the 5th. Big F of x is going to be 4x to the 7th over 7. Done. Sometimes you might need to rewrite it. 3 over 2 x to the negative 3. So big F of x is going to be equal to 3 over 2x to the negative 2 divided by negative 2. When we divide by negative 2, we get the following. Write this down here. Get 3 over negative 4x squared. So you know how to compute antiderivatives. So how do we do the area? We will say that the area is represented by what we call an integral symbol. The area from a to b of a function dx is equal to big F of a minus big F, or big F of b minus big F of a, where big F is any antiderivative of f. Are you confused? Hopefully not. If you are, we'll bring you through with this example. X squared looks like that. This means that we would like to find the area from 0 to 2. Starting at 0, going all the way over to 2. No need to draw triangles or rectangles or anything. We simply just shade it in. In order to find that area, it's very simple. All we do is we first find an antiderivative, x cubed over 3. We draw this bar, and that means we evaluate it at 2, and we evaluate it at 0, and we subtract. When you plug in 2, you get 8 over 3 minus, then plug in 0, and you get 0 over 3, or 8/3. That's the area exact. So look again at the fundamental theorem of calculus, part 2. It says, in order to determine the area from a to b of a function, simply find an antiderivative, evaluate it at the top, and then evaluate at the bottom and subtract the 2. That's it. We look at the next one. Looking at 3x squared from 4 to 2. I like to draw a little graph. You should always draw a little graph to verify that you are looking at the area correctly. 3x squared is going to look something like that. I'm looking from 4 to 2. So that's the space we're looking at. Simply find the antiderivative. It is x cubed. Evaluate it 4 and 2. 4 cubed is 64. 2 cubed is 8. We subtract them, and sure enough, you get 56. Want to check your answer? Easy peasy. Go to your calculator. Turn it on. Go into y equals. Type in the function 3x squared. Delete, delete, delete. Zoom standard. There's your function of 3x squared. Now I'm going to determine the area. Press second calculate to get to this screen where you have value, 0, minimum, maximum, intersect, and then number 6. Number 6 is the derivative. Number 7 is the integral. You can check your answer by plugging in the lower limit, which is 2, and the upper limit, which is 4. And it will draw the shaded region, and it comes out to 56. This is 3x to the 1/2. So the antiderivative would be 3x to the 3/2 divided by 3/2, or multiplied by 2/3. 3's cancel. I get 2x to the 3/2, and evaluate it at 2 and 1. When we plug in 2, we get 2 times 2 to the 3/2 minus 2 times 1 to the 3/2. 2 to the 3/2, 2 to the 3rd is 8. Square root would be 2 roots of 2, so 4 roots of 2 minus, and then 1 to the 3/2 is 1 minus 2. We'll just leave it like that, but that is the answer. As you check out the area, you can see 3 roots of x is going to look like that. Evaluating from 1 to 2, that's the area that you just determined. Let's try the next one. X to the 4th over 4 minus x cubed over 3 plus x squared minus 3x. That's the antiderivative. We will determine the integral at 1 and at 0. If I plug in 1, I get 1/4 minus 1/3 plus 1 minus 3 minus, then plug in 0. I get 0. Common denominator, 12. So I have 1/4, which is 3/12 minus 4/12 plus 12 over 12 minus 36 over 12. 3 minus 4 is -1 plus 12 is 11. 11 minus 36 is -25 over 12. Notice that this area is negative. You didn't think you could have negative area, but in calculus you can. If you were to graph that, which you should check on your calculator, y is equal to x raised to the 3rd minus x squared plus 2x minus 3, and I zoom 6, notice the shape that you get. It sits below the x-axis from 0 to 1. It looks something like this. Okay, so if you check out 1 to 0, that is the area you're finding. If area sits below the x-axis, we deem it to be negative. Two more examples. We have sine of x. What do you take the derivative of to get sine? This is confusing for some people because if you say cosine, you're incorrect because the derivative of cosine is negative sine. The derivative of negative cosine is positive sine. So the antiderivative of sine is negative cosine. You have to think it through. I evaluate at pi and at 0. So consider 0, which is the coordinate 1, 0, and pi, which is the coordinate negative 1, 0. We first plug in pi. What is the cosine of pi? It is the x value of negative 1, make it negative, and I get positive 1. Minus, now we go ahead and plug in 0. The cosine of 0 is 1, make it negative, negative 1. Sure enough, 1 minus negative 1 is 2. That is the area of sine of x. If you consider sine of x, it looks something like that, where this is pi, and this is 0, and this is 2 pi. You can see that the area sits above the x-axis from 0 to pi. So it should be positive. Last example, 2 over x squared. I'm looking for the area from 1 to 5. Check it out. Draw it just like so. Is 5 over x, or 2 over x squared looks like that. We're going from positive 1 to positive 5. Looks like the area should be positive. This is 2x to the negative 2. The antiderivative would be 2x to the negative 1 over negative 1. Or if you were to write that, negative 2 over x. And we would evaluate it at 5 and at 1. Plug in 5 and we get negative 2/5. Plug in 1 and we get negative 2. So you have negative 2/5 minus negative 2. I'm going to add that and you get negative 2 over 5 plus 10 over 5, which is 8 over 5 or 1.6. Again, if you'd like to check your result, go ahead and plug it into your calculator. You have, in fact, 2 over x squared. 2 divided by x squared. As you calculate that area, which is number 7, you would check 1 and you would check 5. 1.6. There you have it, folks. That should be able to take you through your worksheet. Well, actually take you through the one after that. It's time for you to practice finding antiderivatives and using what we refer to as the definite integral. Fundamental Theorem of Calculus, Part 2. Way to go. You know how to find area. See you soon.